housekeeping. Jump right in. We went to the creek this week and in lab, and so there's some questions that you're going to answer. Now there's numerous sources for where you can get answers. One place would be the water report. I'll go there first. And so if we go on to Campus Web and we go to your course, there's an actual 2013 that's posted. You can find newer ones if you would like, but there are water reports. Let me get the handouts where I want to be. And if we go down to our current unit, then what you can find is a 2013 water report. And in that water report, it's the one that was published that year. And I grabbed that and put it up. I'll try to refresh that. I may try to do that this week. But if you use this one, it's okay too. Okay? Because the numbers, do they change much over the years? You hope not. Okay? Unless they improve, but generally they're pretty fixed. And so if we go down and look at them, then this gives alkalinity, aluminum, calcium chloride, hardness, iron, magnesium, pH, potassium, sodium, sulfate, total dissolved solids, and zinc. Okay, those ions. Now there's one that's missing there. What's one that you guys did that's not on that list? The phosphate ion, right? It's missing, so you'll have to find that from another source. Okay? Now, if we go up, I talk about some other things that were monitored or regulated contaminants, and barium and the nitrate, nitrite are monitored, right? And we also have the disinfection byproducts, the TTHMs and the HAA5s, and we see that they're well under the maximum contaminant level. In fact, everything that we have here is usually that way. We also have carbon total organic carbon. Now that actually leads to another number which you could measure, which is biological oxygen demand. And there's a test protocol which you incubate the water at a given temperature and then run dissolved oxygen tests before and after, determine how much oxygen was used up by the carbon that's in the water. And so those are connected in that fashion. And then we have copper and microbiologicals. And so what we find is that our water here at College of the Ozarks is actually really good water in terms of produced in a drinking water facility. Okay, so it's a good thing. And we're blessed with that. I know that sometimes it seems to have a funny twang to it. That's actually related to seasonal algae that grows. And for example, there's a geosmin late fall that is a known smell, and it can't be removed with the system we have. You have to use an activated carbon filter, and they're actually quite expensive to operate. The molecule itself doesn't cause any health issues, so we don't remove it, right? But that's that funny taste and smell that you get in the fall. Have you ever noticed that? We haven't had it this year. They're moving a lot of water this year because of the high levels in table rock, and so it prevents that from forming when we have good water flow.
I don't drink the school water.
Oh, you should. There's nothing wrong with the school water, let's put it that way. Okay. All right. So anyway, so there's that information. Another source that I'm going to show you is Missouri Stream Team. You could also do MDR. They have data, and then the USGS, right? The United States Geological Survey. They actually have huge amounts of data available. It's a little hard to sort through, and their search engine is takes a little practice to get used to. Does that make sense? But it's actually the best source. But Stream Team is something that has been built that everybody can kind of participate in, and to learn about how to sample water. And then I'm going to go down and looking at training materials and resources, and we're going to go down from there and find quick reference guides and SOPs, or you could actually do their field PowerPoints, and so there's information in those. But I wanted the water chemistry ranges, and so for normal Missouri streams, this gives you kind of that background data. Troubleshooting water chemistry. We talked about how important that is, right? And that when we had a reading that was unexpected, that we should recognize that, and if we're doing this for a study, then we would remeasure, okay? And so water temperature range, well, we have a fairly wide range in terms of water temperature. When water gets to 0, what happens? It freezes. Yeah. Dissolved oxygen from 5 to 15 milligrams per liter. The colder the water, the higher the oxygen, especially if it's turbulent. All right. That's why fish like trout, they have a very high oxygen requirement, and so they live in cooler water. All right. And you can see that on a nomograph. Moore's nomograph was often used to estimate the dissolved oxygen in a stream based on temperature. And we used those back when I was in college. All right. The pH should be between 6.5 and 9 for a normal stream, right? So I suggested that the 7 to 10 standards were good standards for what we were looking at. And we didn't do conductivity, and we didn't do nitrogen or ammonia, but we have phosphate here. And in the Ozarks, 0.2 milligrams per liter or less is a normal reading. But in fact, the Taneycomo White River system, those numbers actually should probably be under 0.05 during this time of year, because the water's warm enough that things are actively growing, and so that phosphate level should be much reduced. Okay, so just throwing that out there, that could you use this as a source? Absolutely. All right. So just trying to get you guys involved, and I think that this is a neat organization. I'm not currently participating in it, but I have in the past. Okay, does that make sense? Yeah. All right. Any other questions about homework or lab work? Yeah.
On our third run for Thursday's lab, for hardness, it was very high. Do you want us to include that in our average?
It's up to you. Okay, but if you don't, be sure to note why you didn't. Okay. Usually with just 3 data points, we have to keep that, and you just have a much larger standard deviation. But with as big a gap as what we had, then you could probably justify letting that go. And so we haven't got the statistics. Take quantitative analysis, and we'll improve your skills there. Okay. Anybody else? No? All right. Just to let you know that on Campus Web, I did go ahead and put all the categories in. Some of them you can't see yet because I hid them from you. So you wouldn't be asking me why you didn't have a final test score yet. But they're all in, and then I weighted each category. The lab quizzes were actually entered as quizzes, and I changed them to all be lab reports. I hope that's not too confusing, but that puts them in the laboratory category, and in that 35% of the grade. Okay? And then the normal tests and quizzes, I've labeled them as tests. All of them are tests now. And so those scores will be in the test and quiz category, and they're 25% of your grade. The homework then as another category, and I'll download those during week 8 midterm, and they're weighted 15%. And then the final exam, the one test, is actually 25% of your grade. And it is a comprehensive test over the entire semester. Okay? Cool? Yeah. Next semester, and we actually have study guides for this. We have 3 new ones. There's a second edition now, and I still have the older ones too. But we do a standardized test. It's the American Chemical Society General Chemistry exam, and we use that to do departmental assessment. And so we'll have that test for you guys, but it actually covers 2 semesters of content. So this semester and the following one, General Chemistry 2, are on that exam. And it shows you guys where you stand in terms of the nation. So be aware that if you're staying in General Chemistry, that's coming. You can get your own study guide from the American Chemical Society. If you just search it online, then it will take you to that site where you could order that if you'd like your own guide. But it's a good review book. it has problems from each type, and gives some strategy in solving those and those types of things. Okay, cool. Any other housekeeping? No? You guys are way too quiet today. I can hear a pin drop. All right, so I think we finished the problem with aluminum plus oxygen going to aluminum oxide. Did we do that? Or do we have more problems to solve in that? We finished that and I pulled up a picture of the railroad iron. Is that correct? Not yet? Well, how about this slide? Stoichiometry, 3 steps. Do what?
I think you're about to talk about.
All right, I just want to make sure that I was in the right place and don't want to leave something out. Is this on the road map? It is, isn't it? Convert given measured amount of substance into moles, and then convert the moles to the next compound, compound A to compound B, and then convert this into an answer. All right, so this is kind of simplified in that and isn't showing all the different routes. But this is our strategy to solve all of these problems. Now, when we get into problems, for example, on sapling, then sapling loves to do fun stuff like this. And we'll set this problem up. How much iron-3 oxide and aluminum powder required to field weld the ends of 2 rails together? All right, now to get to this, you need a couple things. Number one, you need some information about a weld and how much weld we're going to need to make that work, right? And so this gives that to us, and it says the rail is 132 pounds per yard, and that 1 inch of the rail will be covered by an additional 10% mass of iron. Okay, so that means that if we can get to 1 inch of rail, then we would know the mass of that, right? It would be 10% additional, okay? Or if we want to look at that then in this way, then mass of iron in 1 inch of this rail is 132 pounds per yard, right? And then 1 yard times 36 inches, and then times 454 grams per pound. What did I just do there? A whole bunch of conversions, didn't I? Does sapling like to do this to you? Does this have any connection to the mole problem that we showed on the previous slide? It's getting it to units that we can calculate moles in, okay? And so they have you do this because real world problems sometimes start in this fashion. Now, what I want to show you actually right now is a video. You guys like videos? Yeah. And so this video is, I always love it. It's like Jorgensen. Well, we'll get there. But this is rail welding. Okay, this is overseas, but the video is great in my opinion. If I can find the enlarge button full screen, and we can go right here and hit. So, notice we have no electricity, right?
Customize and save with Liberty Mutual. Shocking, right?
Just like the faculty roasters. What do you guys think? Anybody know that reaction? No? So you can't write a balanced chemical equation? Did you see the result of the reaction? It's actually a pretty popular demonstration. There's been people who've done that inside and burned holes in floors and caught things on fire and those types of things, because when you have molten steel, right, and it lands on something that's flammable, what's it do? It catches on fire, doesn't it? Yeah. So very cool reaction. It's called the thermite reaction. Thermite welding is what they were doing there. Have you ever wondered how they built the railway all the way across the United States long before electricity was available? Or Europe? How did they put the tracks together? Sometimes they bolted them, but if they're welded, then this is the way they were welded. This reaction's been known for a very long time, right? Kind of cool.
How they figure it out?
Chemists are cool. Yeah. That would be my guess. I mean, somebody literally it was combining things, and
I don't know if it was like an accident.
that could have been. I don't know. I don't know if it's serendipitous or if it was intentional that they knew the reacting ratios and those types of things. I don't know. That's a great question. Not sure. Back to PowerPoint. All right, so you guys can see that weld up here, and so the way to make that weld, or one of those ways to do welding in remote places, is with a thermite reaction. Okay, so it makes. Well, wait a minute. Does that mean we know one of the products? Can you help me there? It's probably not oxygen, but iron, right? Because we're putting iron into an iron track, right? You guys with me? So one of the products is iron. That means we need a source for the iron. Any ideas? Iron oxide, Fe2O3. And believe it or not, the other reactant is aluminum, okay? So what do you think the slag is, the other component that's produced? Aluminum oxide, right? So, are we balanced? No. Fe2, so I need 2 over there. I've got 2 aluminums there, I put a 2 right there, now am I balanced? Yeah, so we have a reaction, right, where we take aluminum and we convert it to aluminum oxide. Thought that was given there somewhere, so there's our reaction that we're gonna use, just to let you know that, to make sure we're in the right place. And so anyway, the question, I'm gonna give you guys the first conversions, and I want you to go right to this number right here. The mass of iron in a weld with 10% mass is the total mass, right? Times the 0.1, the 10%, and that gives us 167 grams. So if I start with 167 grams of iron that I need to make, so what I'm saying, gosh, that's an ugly drawing, is that I need to make 167 grams of iron, right? You guys with me? How much of these two do I need? Is this kind of what we've been doing? Yeah, instead of starting with the reactants, we're just starting on the product side and we're going the other direction, right? It's not any different. What's your strategy? What's the strategy? You've got grams of what? A. You're going to convert it to moles of A, and then from moles of A to moles of B, and then from moles of B to grams of B. And you're going to do that twice, right? You're going to do it once for the B aluminum and once for the B iron oxide. Okay? So you have two calculations to do here. I want to let you try and start those. Get your calculator out, work along with us. Okay? Work ahead of me. Please, please, please set that up. Set that up. Iron, 3 oxide, aluminum powder required to field weld the ends of 2 rails together. pieces on the board. And then we need that number up there down here. Does anybody have that calculated? Iron oxides, molecular weight? $238.7. So it's 239 grams per mole.
Oh, grams per mole.
Huh?
Grams per mole is 159.
Well, 159. My bad. All right, so I've got the calculations set up there, and I'm starting with grams of A, right? And so the step right here is convert to moles of A, and then I convert from moles of A to moles of B, and then I convert from moles of B to grams of B. Right. If I check, like I didn't do on Wednesday, if I check my units, then grams of Fe cancel here, my moles of Fe cancel here, my moles of aluminum cancel here, and I'm left with grams of aluminum. Okay? You should do that every time so you don't make that mistake that I made, right? That's amateur, that's beginner. Okay? So 167 grams of Fe times 1/55 grams per mole of Fe, and then once again our moles of Fe cancels, and moles of Fe2 cancels, and we now have grams of Fe2O3. All right? Yeah, everybody good? Sure. All right, does this take a little practice? Yeah, we're starting to put together some music now, right? We've been working on the pieces, learning how to play the chords, and now we're trying to put it to a little bit of music. And so 238 for the bottom one, for the iron oxide, okay, is what calculates. And everybody done with the second calculation? What am I going to find when I flip this up? 81, everybody agree with 81? Yeah. 80.6, that is 81. So, cool. So that's a basic calculation, mole A to mole B. Now what's it really saying? That bucket, if I need, right, to make 167 grams with the bucket that the welders had, right? Now, did you notice something that was there excess? Do you think that they had exactly the amount they needed for the weld in there? No, they had excess, so they would be sure and fill the weld, and then they captured that and let it loose. So, but we wouldn't have a known amount that we would need. We would mix that ratio of reagents. We would put them in the bucket. You notice they lit a fuse. It was very hot with a torch. They put that in the bucket, walked away, and let the reaction occur. Cool. And what did it make? Molten iron, right? And so that molten iron then filled the weld. The aluminum was the lighter stuff that was on top. The aluminum oxide is much less dense than the iron, and so it floats to the top, just like other things that don't mix and are less dense. You guys with me? And so it floated to the top, and they beat the slag off with the hammer and the press they used to pinch the steel that was still hot, so it would be easier to beat off with a hammer and then grind it down with the grinder. Cool? I think it's kind of a cool problem because you can actually see that happen in that situation. All right, this is one of my favorite slides. And you're going to laugh when I roll this up. It's about limiting reactant. And it's actually this one is the one that I want to look at. It's my favorite slide. I thought it was that one. Reactant that limits the amount of product that can be made. Okay? I think that this does a better explanation when I start talking about over here in a chemical reaction and I start using the word limiting reagent, that you guys tune it out because it's chemistry. Okay, you guys with me? You guys see that happening? So this slide puts it into language that we all can understand. Right? And so what a limiting reagent is it limits the amount of something that can be made, right? And this is talking about making pamphlets, right, or booklets, or whatever you want to call them. It uses the word pamphlets. And so it says that you had 400 yellow sheets. You have a stack of them. They're sitting right here on the bench. And to make our pamphlet, we need 5 of those per booklet, right? How many total can we make with 400 if we need 5 of them? How many can we make? 80. How did you get there? How did you do that? You knew the amount that you needed to make one, right? Kind of like we did there, we knew we needed 167 grams. You guys with that? Right? So here we know we need 5 to make a book. And so you say that if we need 5 to make a book, and we have 400 total pages, right? What did you guys do? Did you just divide? Yeah, 5 into 400, and that equals 80. Okay? We have 300 blue sheets, and we need 3 per pamphlet, right? What are you going to do there? Take 100 and divide it by 3, right? Or no, 300 divided by 3. Excuse me. I just gave the answer, right? So that means we could make 100. You guys with me? Yeah. And then we have 400 pink sheets, right? And so 400 pink sheets, we need 2 of those per sheet, and so that's 200 pamphlets that we could make with the pink. Okay. Which one of these is going to limit the number of pamphlets that we can make? It's easy, isn't it? The yellow one. It's obvious, right? For a chemist, we see the same thing with a chemical reaction. If we know the number of moles of each that's required, right, then it's just like having pages for a pamphlet. Does that help? Yeah, I hope that it does, because it's kind of a conceptual thing that we're trying to get you to step up on. And so when we're doing these calculations, now the last one we weren't doing, we calculated the exact amount, right? The theoretical amount to make the exact amount of product. So if I'd had extra iron, more than the mass that we calculate, or not more iron oxide than the mass we calculated, then it would have been in excess and we would have been limited by the aluminum metal, okay, or vice versa. And so it's the same thing there. Now, and we can go on and we can say that if we make 80 pamphlets, then we're going to have 60 blue sheets left over and 240 pink sheets in the same fashion that we did this. Okay, we can calculate how many we actually used and then how many are actually left over. Chemistry does exactly this. This is how we use balanced chemical reactions to find things. We have limiting reagents, we have the reagents that are in excess, okay, and that are remaining after the reaction happens, because we only need so much of each one based on the balanced chemical reaction. Cool? Yeah. All right. So this is a very simple problem that's doing it in chemistry language so we can do all the math in our head. Okay, you with me? All right? And it's not starting at grams to confuse things, because, well, in reality, when we measure things, we either start in grams or we measure with volume, and so when we measure in those ways, that we have to convert from grams to moles. When we measure with volume, then we need a concentration to convert to moles. Right? But it's the same fashion. So taking out those steps on either side, I'm looking at the middle step, where we go from moles of A to moles of B. Okay, you guys with me? And in this, I've got what is the number of moles of calcium sulfate that can be produced by allowing 1 mole of SO2, 2 moles of CaCO3, and 3 moles of O2 to react? Right now, we're going to practice something else. I want you guys to write a balanced reaction that would account for what we're about to decide. Okay? So I want you to try to write a balanced reaction. You're given the 3 reactants. The 3 reactants are SO2, CaCO3, and O2, right? And then your products at the top. Are you finding a problem? What's the problem?
There's not a carbon.
There's not a carbon. There's a little bit of chemistry I'm going to teach you right now. If you ever see carbonate, right? So the compound calcium carbonate is in there, right? Whenever you see that, and always think of one molecule in a reaction. Anybody know what it is? CO2. Okay? Could be CO2, but I mean, yeah, CO2 is your best bet. What's the last thing you should balance? I'd probably do the oxygen last because it's by itself, and so you can make an adjustment on one thing. How you doing? Definitely you're going to need more, right? Because there's 6 oxygens on this side and 7 over here. And then, but the issue becomes when I start changing things. So if I put a 2 here, right? Then where else do I need a 2? I need one right there, right? And when I put one right there, I also need one right there. And so now I've got 2 calciums. Alright, 2S, and still have 1 C. Whoops, I need a 2 there too, so now I've got 2 C's. And 2 times 4 is 8 plus 4. 8 plus 4 is 12 oxygens. And so let's go over on this side. Now I've got, I started calcium, do the same, 2 calciums. And I've got 2 sulfurs, I've got 2 carbons, and I've got 2 times 2 is 4, plus 6, plus, and then 2 more is 12. Guess what we just did? Huh? We balanced it, didn't we? Yeah. So now we have a balanced chemical equation, and so the next thing is to answer the question. Okay, what's the question asking? how many moles of product calcium sulfate can be made from 1 mole of SO2. Now, what it's saying is that I have extra of the calcium carbonate in the oxygen. Okay? If I have 1 mole of SO2 and it's limiting me, how much product can be made? How much? I have 1 mole of this. How much of this can be made? 1 mole. Right? For every 2 pages of this, I can make 2 pages of this, right? So if I only have 1 page of this, how many of these can I make? 1 page. Cool, you guys with me? All right. And so then the next one is, if I start with 2 moles of calcium carbonate, if I have 2 of these, how many of these can I make? 2. 2 pages of this to 2 pages of that. If I have 3 moles of oxygen, how many of, is that what it says up there? Yeah. 3 moles of oxygen, how many of these can I make? 6, right? 3 times 2 says that I can make 6 moles of this with the oxygen. Right? Now, I'm going to ask this question, which of these is the limiting reagent? Which one limits the amount of product that can be made? This which can make 1 mole, this which can make 2 moles, or this which can make 3 moles? Or 6 moles, excuse me. The SO2 is the limiting reagent. That's one that defines. In which ones will we have extra pages of if we use those amounts? The calcium carbonate and the oxygen. Which one is in the most excess? The oxygen, right? Have a whole bunch of extra oxygen. Does that help maybe to think about limiting reagent from that direction? To think about pamphlets or booklets and then think about moles are the same type of thing. It's an accounting, isn't it? So, all right. So this just goes on to show what we just did. And so how much can we make? The answer to that very first part of the question is what is the number of moles of calcium sulfate that can be produced from those amounts of reactant? The final answer is 1 mole. Okay, of the SO2. Determined by the limiting reagent. Right, determined by the limiting reagent. Any questions on that? Could you convert each of those numbers up there to grams, the SO2 and so on, if you had 1 mole of that? You guys have that ability, right? So if you started with grams and you can convert it to moles, okay? So we're just going to be working back and forth on that. All right. Now, we're going to use some of these calculations, and actually we're going to do this in lab. We'll do percent yields, whole bunches of them over the years. All right. And so this is a calculation where you're going to use this type of calculation to find something. Now, the actual yield actually comes from the laboratory, right? You go in, you synthesize something, right? You have so much starting materials, and you make a product, you weigh the product. You guys with me? That's how you get an actual yield. It's literally the weight of it. The question becomes, how do you get a theoretical yield, right? And so that means that we look at a reaction like this, and we look at what we are starting with, right? And we look at how much we can make 1 mole of this, and that would be the theoretical yield in moles. Okay? And so these look, well, just like what we're doing right now. All right. So the amount of product produced by reaction based on the amount of limiting reactant. Okay? And the actual yield is the amount that's actually produced in the reaction. And so here is a problem where we're going to calculate a theoretical yield. And it says a rocket fuel, hydrazine, is produced by a reaction of Cl2 that is reacted with an excess of sodium hydroxide and ammonia. What theoretical yield can be produced from 1 kilogram of Cl2? Okay? I'm about out of time, so I'm going to give you the reaction and not have you try to write that. Okay? So there's the balanced reaction. And what I want you to do is it's giving you how much can be produced with 1 kilogram of Cl2. What does that mean for the other two reactants when it's asked in this way? They're in excess. It's giving you the limiting reagent in this, okay? Sometimes you're going to be asked to determine the limiting reagent, like we did in the last problem, okay? Sometimes it's like this. It gives you the one that's going to be limiting and calculate from there. So I want you guys to try to calculate the yield, the amount of product that can be made, theoretically, from that many grams of Cl2. I have a question for you right now. All right? 35.5 times 2 is what? 71, right? So I just calculated the molecular weight for Cl2, okay? But I have a question. Can I write it, right, as 1 kilomole over, right, 71 kilograms to do the conversion? What? Can I do it that way? We normally use the units grams per mole, right? Did I multiply them both by 1,000? So this is legitimate and it makes it easier to do sometimes. We're just going to work in kilomoles instead of moles this time, right? So don't be confused by that if you see that, all right? So I can use millimole, I can use nanomole, I can use whatever that may be, nanomole, nanogram, millimole, milligram, so on. And you'll see that in a lot of calculations. All right. So, products in blue is the N2H4, right? What do we need next? We did a conversion to moles. We need a mole ratio, don't we? What's the mole ratio? 1 kilomole into H4, excuse me. As long as I wrote it. 1 kilomole Cl2. And then what? I've got grams of A to moles of A to moles of B. Now what? Moles of B to grams of B. So 28 plus 4, 32 kilograms per kilomole. And so now if I cancel my units, kilograms, moles, and my answer's in kilograms. So we have solved this problem, right? We're going to review this next time, okay? And I'm out of time right now. And 0.451 kilograms of hydrazine. But then the next question, we're going to look at if we have an actual yield, and we're going to calculate the theoretical yield or percent yield from the actual and theoretical. Okay, so that's what we'll do. And then we'll have one more math problem. We'll finish this chapter up on Monday. Okay, and we'll be starting into chapter 5.